Today we are talking about the very last problem type of the whole year, and it is circuits again. And you're like, I thought I finished the circuits unit. Haha, no you did not. We are going to get the most complicated, well maybe not the most complicated, most conceptually complicated circuit types that you've seen so far. Alright? The reason it's conceptually complicated is because we now have to throw inductors in. Alright, so we've talked about batteries, we've talked about light bulbs and resistors, we're talking about wires, and we talked about capacitors. And the last circuit element we have to throw in is inductors. And by the way, this complement of everything, batteries, wires, resistors, light bulbs, capacitors, inductors, all falls under the category of like passive circuit elements. It's like if you take a circuits class, this is the first type of things that you will talk about. Then later on in circuits class, you'll get to more complicated equipment. But this is like the canon of the basic stuff. All right, so you will have complete basic circuit knowledge after today. All right, you guys ready? Let's do it. All right, so the first example is if we take a simple series RL circuit. What does RL mean? What's the R stand for? Resistor. What's the L stand for? Inductance. So RL means resistor-inductor circuit. And you can see it right here. It's got a battery, a switch, a resistor, and an inductor. Okay, so here's the concepts part. Dino, how smart are you feeling today? The usual. The usual. Oh, that's pretty smart. I think you can figure this out. All right, you ready? Here we go. Let's see. So this switch is initially open. So how much current is flowing in the circuit when the switch is open? None. Okay, good. So we got that. What happens when you close the switch? Starts flowing. But the instant after were you here yesterday? And we talked about inductors? And you saw what happens when you go, and you saw the arky-sparky? Why did the arky-sparky happen? What does an inductor hate to do? No, it's okay with changing voltage, but it's not okay with changing the amount of current flowing. So if you close that switch, how much current flows? No, not at all. None. Instantly, the instant after you close the switch, none. But then what happens? And then it builds up, right? So, yeah. So it takes a certain amount of time for the current to get going faster and faster and faster in the circuit because it's got no magnetic field initially in the inductor, right? And if it's got no magnetic field, no current, no nothing, right? And then you try to force it to have some current to flow, it's going to be like, whoa there, hold on. I can't do this right away. I got to build up my magnetic field first. And so it takes a while. All right, so RL circuits are these really weird circuits. They're these really weird circuits that take a while to build up current. Or what would happen on the other end if you had it going for a while and you opened the switch? It would kick and buck and fight. Why? Because it would try to maintain that current flowing. And actually what's happening as you're opening that switch, it's going to still force the electrons to jump the gap. It's going to be like, no, I'm not going to stop! And so you get this spark as you open the switch as that current is still jammed over that gap. And it's this crazy effect. And you saw that yesterday, right? You saw the sparks happen. All right? That's why. It doesn't want to change the magnetic field inside of itself. It doesn't want to change the current. And so you get these just crazy sparks flying as it like forces the current across that gap, the air gap, right, as you're opening the switch. All right, so really cool effects with inductors, and really useful too. All right, so now, basic scenario, it starts off no currents flowing. So the instant after you close the switch, how much current flows? 0, and then it ramps up. By the way, it's the buildup equation, right? And as time goes on, eventually it builds up, the current builds up, builds up, builds up, builds up until it's at the value it's going to be at. All right, so at time equals infinity minus, current would reach some steady state value and the voltage. Is infinity minus even technically okay? All you calculus nerds, what do you think? Infinity, right before infinity? I just made that up. I don't even know if that's okay, calculus-wise. What I meant was after a really long time. Yeah.
Well, no, it's not infinity minus, it's just a dash. If you notice, there's other dashes behind them.
Oh, it's just a dash. Oh, okay. Can't even read my own notes. like it, the limit as it approaches infinity minus. Infinity minus 1. Yeah, so I'm an idiot. All right, moving on. You never know. You never know in these notes. Sometimes they're a little sloppy. All right, so anyway. So voltage difference across the inductor. Ooh, this is a good one. Let's say initially, if there were no current, and let's say your EMF was like 12 volts. So the bottom's at 0 volts, the top's at 12 volts. Yeah, that means it's 12 volts here and there's no current. If there's no current through this resistor, what's the other side of the resistor at? 12 volts. So it's 12 volts here, 0 volts here. All right, and then as the current starts flowing, it starts flowing and starts flowing. Guys, shh. As the current starts flowing and flowing and flowing, the voltage across the resistor increases, so the voltage across the inductor has to decrease. All right, so here we go. So you get these decay for voltage and buildup for current. And of course, do you remember the decay and buildup equations? Decay was, what was the decay equation? V equals V max e to the negative t over tau, right? So it goes, and then the buildup is I max, and then 1 minus e to the negative t over tau. So that's buildup. All right, so here we go. So we're going to derive the decay and buildup again. All right, so here we go. Proof. Current buildup and voltage decay. This is a little trickier than it was for our C circuits, so pay attention. All right, so here we go. Kirchhoff's voltage law, if you start in the corner and go around, you've got the first thing you see is the EMF. The next thing you see is losing voltage across the resistor, so minus IR. And then the last thing you see is losing voltage across the inductor. But the voltage across the inductor is L di over dt. And then equals 0 when you get back to the start. So the equation is, I would divide everything first through by L. Everybody got that first trick?
Yep.
Because remember in an RC circuit you wanted to have R times C? It turns out in an RL circuit you want to have R divided by L. So divide by L. So you got EMF over L minus I times R over L minus di over dt. Put the di over dt on the left. You get that. Combine like terms to get L on bottom. Now we want to get rid of the R in front of the I. You don't actually technically have to do this right here, but if you don't, then you're going to have to do a little trickier U substitution. So I get rid of the R in front. So it's R over R, EMF over R, and L over R. Do you see why you can do this? You're dividing the top by R and the bottom by R. So that's one of the tricks you got to know. So next, get all the I's on the left and the T's on the right. Integrate. Do natural log stuff. and you end up with I equals EMF over R times 1 minus e to the negative R over L times T. Okay, so is I buildup or is I decay? Is this buildup or decay, this one?
Buildup.
That's buildup. What's the time constant? Because remember, it's T divided by tau, right? So what's the time constant? No, it's not R over L. It's inductance over resistance. All right, this is interesting. If you have a bigger resistor, does that make it go faster or slower?
Faster.
Faster. What? The bigger the resistance is, the faster it builds up?
Yeah.
What? What? What?
No,
How does that make any sense? Wait, say that again? Decreases the voltage difference. It makes sense to me that the bigger the inductor is, the longer it's going to take to build up. But why is it the bigger the resistance, the less time it takes?
The less time? Wait, the less time?
Yeah, the less time.
Oh, because current will be less. Will increase less, so then changing current.
How does having more resistance make current build up faster?
It'll...
What? Yeah.
It's bigger resistance, there's a larger voltage drop across the resistance or a smaller voltage drop across the inductor. That's about it.
Doesn't current lead voltage?
At time infinity, there's no voltage drop across the inductor, though?
Yeah, so
How does that make sense?
Current leads voltage, so if you're...
The less voltage drop you have, the quicker it goes. That's so backward in my head. It's so backward in my head. Isn't it backward in your heads too, or am I just weird?
Wait, I thought that...
Wait, let's look at the picture again.
I thought that you'd have a lower
Oops.
current, so then that way the changing current would occur quicker, but then the resistor would slow down current.
So the bigger the resistor, the faster this thing goes.
Well, the faster it would build up, right?
The faster it builds up.
Oh, builds up.
Wow, that's so weird. That's so weird. Means if you had no resistance, it would take forever to build up.
Yes.
Well, because it would...
So weird. I need to ponder that one. That's so cool. I love physics.
Well, actually,
come on!
well, theoretically it would, but since wires also contain some resistance, that
Googling it.
like if you.
All right. So anyway, I'm actually going to move on and let you ponder that one because I want to finish. Oh, the answer is the less the resistance is, the faster it builds. No, the slower it builds up. Or the more the resistance. If you have a bigger resistance, it builds up faster. All right. So moving on. So now for voltage, it's supposed to be decay, right? So and once the inductor goes after a while, it's going to behave just like a wire. Oh, I forgot to mention that. After a while, the inductor behaves like a wire, right? And initially, the inductor behaves like an open circuit. So the voltage difference across the inductor, delta V over the inductor equals negative L di over dt. So negative L d, that whole equation that we just derived up here. So we got to take the derivative of that equation. So the voltage is just the derivative of the current times L. And so you end up with the EMF e to the negative RL over t, which is decay. All right, so fine, let's move on. Okay, so that was the easy one. Now for the crazy one. You ready? Let's say that you had this crazy circuit that just had two things in it. But the two things, one of them's a capacitor and one of them is an inductor.
No.
Oh my gosh. And then let's say that you charged up your capacitor and then hooked it up to the inductor, what's going to happen? Well, initially, what's the state of the circuit? Is there any current flowing initially? No, not at all. Is there any charge built up on the capacitor? Yes. So what's the charge on the capacitor going to do? It's going to try to equalize. So where's the positives got to go? The positives got to go through the wire, through the inductor, right? Now here's the crazy part. So as the positives are going through the inductor, doesn't that mean that it's going to build up field inside the inductor? All right. And so as it's going through, it's building up field inside the inductor. Wait a second now. And so it gets, let's say you get to a point where all the charge is equalized. However, the instant that that happens, do you have any field in your inductor? Yes, you do. So you don't have any charge across your capacitor, but you do have field in that inductor, right? And what's going to happen when you try to get rid of that field in the inductor? It's going to induce a current. It's going to try to maintain that field, and the only way to maintain that field is to keep the current flowing. So you've got this weird situation where your capacitor is uncharged, but the inductor is pushing current through the circuit. Well, no, this is after a while. After the current has built up because all these charges have moved through, now the inductor is full of field and it wants to maintain the existing current. So even though the capacitor is now uncharged, you've got current flowing through your inductor that's going to keep on flowing because it's an inductor. All right.
Does that not depend on which way the inductor is coiled? Because isn't the field different if it goes this way?
Inductors, no matter what, will always try to maintain the existing current.
So is this how AC current is?
Aha! Good point. So the current's going to keep on flowing even after the capacitor is equalized. So what's that mean? So it charges up the capacitor in the other direction. So it jams positive down to the bottom side of the capacitor. Well, after a while, it's like the inductor dies, right? Because it kind of runs out of steam. But now you've got a charged up capacitor again, charged up the other way. So what's going to happen? It's going to do the whole process in reverse again, and then charge up the capacitor so you're at state 1 again. What is this called? This, now, it's called simple harmonic motion.
Oh.
This is called simple harmonic motion. It just goes back and forth and back and forth. And if it is simple harmonic motion, do you know how to deal with it equation-wise? Yes, you have a second derivative equals a negative times a constant times the original value. And you can get the period and the omega and all that of the simple harmonic motion for the circuit. So here we go. So we have circuits doing simple harmonic motion. Here it is. Oops. So we're going to use KVL, Kirchhoff's voltage law again. Basic idea, we're going to start in a corner and go around the loop. Whoop, like that. So starting here, what's the first thing you see? Capacitor. So the voltage across the capacitor, the next thing you see is the inductor. So the voltage drop across the inductor. So you end up with Q over C for the voltage across the capacitor, and negative L di over dt for the voltage across the inductor. But here's the trick, the negative sign. It turns out that positive current flow would cause this capacitor to discharge. So therefore, I through the inductor equals negative dq over dt. I through the inductor would be a negative dq over dt. You've done this you did this in RC circuits as well. Do you remember that? Any charge that flows in this direction through the inductor would tend to decrease the charge on the capacitor. Wouldn't you agree? So positive current decreases the charge on the capacitor, which means that I through the inductor equals negative dq over dt for the capacitor. All right, so we substitute this in for I, and you're left with q over c plus L d squared q over dt squared. There's your second order differential equation. So how do you deal with it? Once it's here, it's really easy. All you have to do is plug the second derivative on the left side. You've got a negative constant times the charge. And so what's your constant? 1 over LC. All right? And what's that mean omega is? What's the angular frequency of this? Square root of 1 over LC. So this thing will do simple harmonic motion with an angular frequency of square root 1 over LC. And so it'll go back and forth sine wave with that frequency. Good? All right. And that's it. That is the last problem type. So what did we do today? 2 different types of problems. RL circuits, which are either buildup or decay, and we did LC circuits, which are simple harmonic motion. Oh, is it possible to do an RLC circuit?
I sure hope not.
Is that like
What would you get? What kind of, would it be a simple sine wave?
it'd be like a flattened or smushed.
No, it'd be a decaying sine wave. It'd start off like this and then get smaller as you lose energy in the resistor. All right? So we're not going to do RLC circuits in class, but conceptually, it's simple harmonic motion with damping. All right, and the reason we're not going to do it is because the math just gets too complicated to test on the AP test. All right, but you can do simple harmonic motion with damping for a mechanical system, like a door, going wop, 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 wop. Or you can do it with a circuit if you stick a resistor in. All right. Oh, by the way, it's also possible to get simple harmonic motion with just 2 capacitors as well. But we're not going to do that. You'd have to arrange the capacitors in parallel and then with a switch. And you can get it, one charges while the other one's discharging. All right. Anyway, that's it.